right. Well, welcome to our next session. I'm Sebastian Sa. I'm the Associate Director of Agricultural Research at the Almond Board. It's nice to see some familiar faces here. And I'll stay around, of course, if you want to chat with me further. So today we're going to talk about soil chemistry, infiltration, and salinity management. That's the next 50 minutes of this Soil Summit event. And to that end, we have aligned a great set of speakers. We're going to start with Ben Needham. He is the president of the La Valle Lab. So he's going to dip a little bit more into soil analysis, what we can get from that, etc. And then we're going to move to two talks from our cooperative extensions collaborators here. May Columber, she's going to start by sharing our latest resource, the Salinity Resource Management, resource that you can pick up from there from the back. And Mohammed is going to then move to talk a little bit of another new resource that we have put together in collaboration with them, the Rootstock resource, an excellent resource that summarizes years of research. And so I'm really looking forward for the next talks that they have and the insights they're going to share with us. And hopefully we can save 5 to 10 minutes for questions. So as you listen all the speakers, think about the questions you want to have for the end. Thank you.
Good morning. My name is Ben Needham. I'm with Della Valley Laboratory, and I want to thank the Almond Board for this opportunity to talk about soil chemistry and water infiltration. Sebastian I appreciate his help and work on this. I've got a lot of stuff to cover, so I'm going to move fairly quickly. Again, soil chemistry, water infiltration, and then a few comments about soil health. This is a typical soil analysis. I hope you can see the numbers. I can see them here in the back. It may be a little bit difficult to see. Anyway, this is just a typical report. Just all the constituents on the top, critical levels on the bottom. So we're going to jump right into this depth. It makes a big difference on where you pull your soils, how deep you pull them. It depends on what you're after. What's the questions that we want to answer with soil depth? Here you can see we have 3 fields. The first field is sampled at 1 foot increments to a depth of 3 feet. Just looking at our major portion of our root zone. The second field is sampled at 0 to 3 inches. 3 to 12, 12 to 24, 24 to 36. We're looking at specific issues that we had in that field in the top, the very surface. And then the last one is down to 5 feet. You do that for monitoring what your leaching program is doing, where your nitrogen is going. A lot of times for new fields, you want to new plantings and things like that. You want to know what you're getting into and what kind of soil amendments you need and soil physical things that need to happen to prepare that soil for the crop. SP is soil texture. What's our soil texture? Generally, they range from 20s, and the 20 range is sandy loams. Heavier numbers, the higher numbers in the 50s to 60s are clay loams, and then the whole range in between. You can see here, if you look at the field number 1, we've got a soil layering. One part of the thing to look at in soil texture is do we have a soil layering issue within the field or within our profile? Soil layering can affect water infiltration. If you've got a heavier soil over a lighter soil, that water will tend to back up. You also have the other situation where you have a lighter soil over a clay loam or a heavier soil. Again, you may have a situation of water perching on those layers, depending on the infiltration rates. And then also here you can see this SP was 39 to 29. That's a pretty big difference in soil texture, but most of that is in the top 3 inches is probably due to the organic matter, not so much in the change in soil texture. pH is important in looking at, a lot of times we have alkaline soils. We're looking at pH. Do I need to reduce that pH? Am I adding sulfur, A lot of growers are adding sulfuric acid to their irrigation waters to deal with carbonates and bicarbonate issues. So it's important to monitor your pH. And then also with that field 2, you can see the pH is at a 5.8. So where did that come from? And it's in the top 3 inches. In this case, it was due to acidic soil amendments or soil fertilizers, ammonium sulfate, those types of things. And in this situation, you don't want to be adding sulfuric acid to amend soil water. We are running into we're seeing a lot of fields where growers are using sulfuric acid to amend the water, and they're not paying attention to the soil pH. So we'll find a soil with a pH of 5.5 in the top foot and an 8 in the second. Now we've got another problem we have to deal with. So it's important to monitor your pH, especially if you're using acidic materials. Also, with that pH, if you're applying acidic materials or sulfur or lime, you want to make sure that you have free lime to be able to interact with that. You can see in that second field there is no free lime. Even though we have some pHs down deeper in the third foot and the second and third foot that are above a 7, yet the buffering capacity of those soils are very low. EC, total salt. EC is a measurement of total salt and what makes up. Those salts are calcium, magnesium, sodium, potassium. May is going to talk about high salt issues, so I'm going to go to the low salt issue. Here we can see we've got an EC of 0.2 in the top 3 inches. And I'll get to that as far that it does affect water penetration. Again, it came from knowing the grower. It came from acidic fertilizers. The grower you can see that there was a lime requirement, and the grower applied the lime and increased water penetration in that situation. So let's talk about water penetration a little bit. Water infiltration. There's 3 or 4 different things that affect that. The first, obviously we talked about SP and the change in soil texture that can affect water infiltration. The second is the situation where you have high sodium levels compared to your calcium levels. In the field 1, you can see sodium is dominant. It'll deflocculate soil. It will affect water penetration. Then you have the alternate where you have very pure soils. And in this situation, field 2, and that's why we did the 0 to 3 inch sample, because we had a problem in that field and we wanted to identify what that problem was. If we had taken a 0 to 1 foot sample, or 0 to 12 inch sample, our pH would have been an average of about 7.1, somewhere in that neighborhood. The EC would have been close to a 7 or an 8. Not really any problems, and the calcium numbers would have been much higher than a 0.25, 2.5. It would have been, you would have masked that issue. So sometimes water penetration issues, especially on coarser textured soils, are in that top, very, very top 2 or 3 inches of soil. Compaction can also be a problem in that area of soil. Okay, so calcium, magnesium, sodium, we have the good salts and bad salts. Calcium, magnesium being your good salts, your detrimental salts are sodium and chloride. And then ESP, exchangeable sodium percentage, is a number that looks at how much sodium you have on the clay exchange sites of your soil particles. And for almonds, right in the neighborhood of a 5, and we start getting a little bit worried. We think about gypsum application and calculating what those numbers might be. May's going to address that issue, so I'm going to move on. Lime presence. Again, we talked about negative or acidic pHs and knowing where your lime is. It's just a part of the soil analysis. It's a piece of the puzzle. Boron. A lot of people are afraid of boron. There are a number of soils where boron numbers are high, especially for almonds. That can be a problem. But I run into a lot of issues where we have boron deficiencies. So boron, you need to, soil is just one piece of the picture here. If you want to evaluate boron, you need to look at your leaf tissues and your almond hole samples, and use all those to put your boron program together. It also depends on where you pull your soil sample. Different locations may give you a different answer. So you need to look at where you're applying boron, where your irrigation, where your wetted pattern is, and what those numbers will, where you're pulling that soil sample will affect what those numbers may be or what results you're getting. NP and K. Again, the deeper sample here shows that this situation we're leaching some nitrogen. Field 2 and field 1 and field 2 show pretty deficient N levels. Again, you need to correlate that with your leaf sample, because where you pulled this soil sample may not be the only place that tree is pulling your nutrients from. So this gives you a look at what's in the tank, what's in their soil, but we also need to be looking at what that tree is pulling up, and is it getting nutrients from different areas than where you pulled your soil. So that's an important look at it. Again, that's the whole spectrum. Soil health. Sebastian asked me to speak a little bit about soil health. Soil health principles. There's 4 main areas. Maximize cover crop, getting soil organic material there. Minimize disturbance. Can we minimize the amount of times that we're running through the field? Can we minimize compaction? Maximize presence of living roots. We heard a lot about the microbial aspect of that. Irrigation is a big part of that. Making sure our fertilizers are there, things that we need to add to the soil is not there naturally, and then maximize biodiversity. So soil health tests. Soil texture, bulk density really talks about soil compaction. pH, salinity, nutrients, you've already been talking about that. That's what your standard soil analysis is looking at. Are your soils, where are we at nutritionally? And then the microbial biomass and soil respiration, we heard about that as well. Soil health in California is becoming more and more a big issue. Not an issue. It's part of our farming environment. We as California agriculture need to be involved in setting and determining what soil health standards are. Our soils are much different than we see in the Midwest and in the East, and we're using a lot of those tests and evaluation methods, but we need to apply them to our situation. Even within California, our soil health and our climate changes from Bakersfield up to Northern California to north of Sacramento. So the numbers are important, but we need to be able to evaluate those numbers and see what they mean to evaluate, where our soil health is. Thank you.
Okay, hello. So I'm going to introduce the new Salinity Management Guide. It's been a nice collaboration between the Almond Board and UC Cooperative Extension in developing that. So we'll get right into it. All right, so how does salinity impact almond trees? There's basically 2 types of stress. We have what we call osmotic stress and then specific ion toxicity. And so trees experience osmotic stress when the increasing levels of salt decrease the flow of water and nutrients uptake by the roots. Okay, so this osmotic stress might be the initial stress that happens when salts start to accumulate. So the first thing that's going to happen, it's going to be, even if the trees are sitting in plenty of moisture, because of the osmotic potential, if you have more salt, the flow of water moves along a gradient, and so it's harder for the moisture to move along that gradient into the roots when there's a higher concentration of salt. When you have a larger solute difference between the outside of the roots and the inside of the roots. So that's going to be the first indicator. And so when trees experience osmotic stress, sometimes we see reductions in vigor and maybe potentially overall performance for that season. If those saline conditions persist over the long term, over time, the tree is going to lose its ability to exclude the salt from the roots. And it's actually going to start to take up some of that salt into the tree. And that's when we're going to start to see signs of specific ion toxicity. And so when you have specific ion toxicity, that's when you're actually seeing visual necrotic tissues in the leaves, things that are going to affect photosynthesis, the ability of the tree to feed the developing kernels. So in table 1 in the salinity guide, I'll give you a closer view if this is hard to see. This describes the effect of EC on yield potential. And so there's some numbers both for the root zone, the soil root zone, and then also for irrigation water. Just to give you an idea, it's like if you're less than 1.5 with the root zone, or even 1.1 with water, you could expect 100% yield potential. As the salinity increases, we start to see declines in potential yield. So the rule of thumb is that you may experience about a 15% decline in yield for every 1 decisiemens per meter increase in EC above 1.5 for the soil. Okay, so soil and water amendments. So we're going to jump right into this. So Ben gave a lot of really good background on the different nutrients and analyses with the soil. But the purpose of the soil and water amendments is to provide a source of calcium to replace the sodium and remove it from the root zone. So that's why we're applying these soil and water amendments. We also need to make a precise calculation of what we're applying, because when we're adding amendments, we're actually adding salt back to the soil. And so we don't want to apply too much, because too much at once can cause those problems with osmotic stress that I mentioned. So we don't want to over apply our amendments. And so it's important to use those soil and water analyses to determine the correct type and rate of materials that you're going to apply. Okay, so a lot of times we're wondering, should I make a water or a soil application? And so as Ben mentioned, with the soil analyses, it's really important to, if you're doing it for the purpose of figuring out what amendments to apply, to get those 1 foot incremental depth applications, and then to take that sample between that 0 to 3 inches. So that can, what this soil analysis tells you with depth is the extent of your salinity problem. A lot of times, if we've had a recent change in water quality, when we're experiencing a drought, even the canal water tends to really go up in salt concentration. So it's good with the change in water quality to be aware of what's happening. So when our source of water is salty, but that's a recent development, we may just be developing a salt layer, in that shallow 0 to 3 inches. And so we might be able to get away with just amending the water to treat the salt problem. If we're finding that salinity problem is elevated EC down through the root zone, then we're probably going to need to be making larger applications in the form of soil granular amendments. So table 2 lists the different types of amendments, and that can be found on page 7. Basically, amendments are going to be separated into your calcium supplying or your calcium forming, your acidic amendments, okay? And so as Ben mentioned, it's really important to pay attention to the pH, bicarbonate levels, and calcium levels to help you make that decision. The different columns here show what the rates of material would be to apply to per acre foot of water or acre foot of soil. And the units that I'm going to be talking about going quickly through a calculation are in milliequivalents of calcium. So Ben mentioned the need to balance your sodium, your calcium, your magnesium. And so the calculations are for, if we want to remove 1 milliequivalent of sodium, that's equal to 1 milliequivalent of calcium. So they have a chemical equivalency. Okay, so again, we're trying to provide that calcium to replace the sodium and remove it from the root zone. Things you're going to look for in your soil analyses. Okay, this is for soil applied amendments. You need to ask for a cation exchange capacity analysis, so that may not always be given when you order a soil analysis. There are ways to calculate that, but this might be the easiest way for the purpose of this example. Ask for cation exchange capacity, and then you need to know what your exchangeable sodium percentage is. So that was on the example that Ben gave. These are going to be the two important components of doing a calculation. And next, we can go through how to calculate the tons of material per acre foot needed to displace sodium and reduce the exchangeable sodium percentage. Step 1 is on page 7 of the guide. And so again, you need that CEEC and that exchangeable sodium percentage. And so what we're going to do is say, okay, this is our initial exchangeable sodium. So we take that exchangeable sodium percentage. So this is converting that percentage to, it's changing the units so that we know like how much is in 100 grams of soil. So that's what this first calculation is doing. So we would multiply that exchangeable sodium capacity by the cation exchange capacity. And then we're going to divide that by 100. And that's going to give us this value of 5.6. Okay, so the next step, we're going to take that number and we're going to say, okay, this is where we're at. And then we're going to say we need to figure out what the final exchangeable sodium percentage that is our goal. I think I noticed on the Della Valley example that Ben had that they said threshold for almonds for exchangeable sodium is around 5%. For this example, I made it 4%. If our target exchangeable sodium is going to be 4%, and right now we're at 5.6, we need to figure out how to get there. So if we take the same calculation, our final exchangeable sodium by that same cation exchange capacity and divide that by 100. So this is what is going to be our target final. So right now we have 5.6. We're trying to get to 2.4. Okay, so it's as simple as subtracting that 5.6 from 2.4. And now we know that we need to replace 3.2 milliequivalents of calcium to displace 3.2 milliequivalents of sodium. That's when you go back to this table, okay? So we know that if we were going to apply 1 milliequivalent to the soil, that would be 1.7 tons per acre foot, okay, of material. But we need 3.2. So if we multiply 1.7 times 3.2, that gives us 5.5 tons of 100% pure gypsum. But we're probably not broadcasting this across the entire area. So you can adjust your application rate for a smaller area if you're only applying as a band along the drip hose. And so step 4 and step 5 take you through how to make that calculation. And so instead of 5.5 tons, well, for the example here, it takes the whole field into consideration. So the example takes into account a 75-acre orchard for the example. Okay, so water amendments, calcium containing amendments or acid fertilizers may be needed to treat the irrigation water and maintain a good calcium balance in the root zone during the growing season. But Ben brought up some really important points with that is that, when we're looking at how we're going to amend the water, we need to be monitoring the effect that it's having on the soil so that we're not totally depleting the soil of calcium if we're applying acid amendments. Okay, so calculating the rate of water applied material requires knowing the EC, the electrical conductivity, the sodium absorption ratio, which is included on most water analyses, and then the amounts of sodium, calcium, and magnesium in milliequivalents per liter. If you don't have SAR, here's a calculation for how you can calculate it. And then it's good to know this simple sort of back of the envelope way to calculate EC is to sum up your calcium, your magnesium, and your sodium and divide by a factor of 10. And so that's how we're going to do it for this example. And so on page 8, there's a chart that shows you the intersection between your sodium absorption ratio and your electrical conductivity. So you can take your unamended water, the information you have from your analyses on your unamended water, and you can see, okay, so if my sodium absorption ratio is 18 and my EC is right around 1.1, this is where they intersect. And then this chart lets you know, okay, if those are the conditions, then that's susceptible to severe reduction in infiltration potential. What we want to do is amend the water sufficient so that we can get no reduction in infiltration rate. And so the approach with the water is a little different, where you might start with 2 milliequivalents and do the calculation and then see where the intersection is. Okay, so it may take a few calculations, but so first you might try 2, then you might bump it up to 4. So the example on page 8 is for using 4 milliequivalents. The way that you do that is that you take 4 milliequivalents of calcium, and then what you would do is you would go back and say, okay, I started off with 0.4 milliequivalents of calcium, so I'm referring to step 1 on page 8. I started out with 0.4, and what I'm going to do is I'm going to add 4. So now I'm going to take 4.4 plus the magnesium plus the sodium divided by 10. That's going to give us a new EC, okay? And that's also, if we recalculate the sodium absorption ratio, doing the same thing, adding 4.4 in for this number and adding, taking the sodium over the square root of calcium, magnesium divided by 2. Sounds complicated, but just takes a little bit of practice. Then you have a new SAR and a new EC, and then you figure out where that new intersection is. So that's how you evaluate the effect of adding 4 milliequivalents of calcium to the water. Okay, so now we know that we want 4 milliequivalents per acre foot of water. That's 936 pounds of gypsum per acre foot of water. There's been a lot of mention of composts, biostimulants, cover crop amendments. As everybody's been saying, they protect the surface of the soil, they enhance the microbial activity that aggregates the soil, they improve infiltration and enhance the effectiveness of the other amendments. So important to consider, and those resource guides are available for you on the side. And I will take questions at the end. Thanks.
Good morning, everyone. My name is Mohammed Yagmour, and I'm the Orchard Systems for Kern County. And today I'm going to talk about some of the tools to manage soil adverse conditions such as salt and toxic ions. So one of those tools is rootstocks. And when we are talking about rootstocks, usually I get questions, what is the perfect rootstock? Or the general answer, there is no perfect rootstock that will fit all situations. But what are we looking into a good rootstock? So the most important part is the compatibility with the desired cultivar that we are going to plant. We definitely need a good anchorage so we don't lose trees and we are able to harvest them and don't lose yield. Good vigor, because vigor is correlated with yield. Definitely low suckering, and the most important part as a tool is its tolerance to abiotic conditions, such as salty soils, or biotic conditions like diseases. So here's some of those challenges. On the left here, you can see sodium and chloride burn on leaves, Lyme-induced chlorosis, boron toxicity, and here are all or some of the disease and biotic conditions such as root knot nematode, crown gall. So, my colleagues showed the importance of the soil analysis and the irrigation water analysis. Okay, and this is one of the first things to do before you choose your rootstock, knowing what you have in terms of your soil, whether you have salts, extra salts, you have boron in your irrigation water, you have nematode in your soils. So all of that information is important to choose the perfect rootstocks. My colleagues in the past, for so many years, had done in collaboration and support from the Almond board, they did many regional rootstock trials. all the way from the northern parts of Sacramento Valley, all the way to down the San Joaquin Valley in Kern County, and evaluated many traits to manage diseases, to manage salty soils, etc. So when we look at rootstocks, the most important part is here is a table of the different rootstocks. Some of them are available commercially. What I want you to focus on, and I will be talking more about, is the parentage. Parentage is usually related to the genetic background, which if you hear me talking about peach, that means the rootstock parentage was actually a peach such as Nemagard. If we are talking about the peach almond hybrids, the famous one is the Hansen and Brights 5. If we are talking about more of complex hybrids, I will be talking about Viking mainly. And we have the plum hybrids, for example, the Rootback R or the famous Krimsk 86 that is more planted in the Sacramento Valley. So one of the things my colleagues looked at is the tree anchorage. Tree anchorage is very important. This is a picture of a trial that was planted in 1997 down in Kern County. We had a high wind of approximately 75 to 84 miles per hour with quite a bit of rain. What they found out that, most of the Nemagard had the most trees falling off compared to the least was the peach almond hybrids. You can see it here, and the Viking. And this results is still true to this date. This is from my experiment that was planted in 2019 down in Kern County, and you can see here that all the peach almond hybrids are still standing straight, the Viking here in the middle, as well as the Krimsk 86 or the plum hybrids. They are doing very well in terms of anchorage. The other soil challenge we can see in some of the soils, especially on the west side, are chloride and the sodium. And both of them will reduce the photosynthetic areas. Why? Because they kill the leaf tissue after the accumulation in the leaf tissue. My colleague, Roger Duncan, worked extensively on that. And he showed clearly that the peach almond hybrid here, do much better in such soils compared to the peach or peach hybrids. So here is the commercial names, but here I'm talking about the parentage. When we look at the sodium follows similarly when we are talking about parentage, the same way as we see in the chlorides. So all the peach almonds are here, and they significantly less compared to the peach. My colleague, Catherine Jarvis Sheen in Yolo County, she did her experiment looking at boron toxicity. So in her case, excessive boron was a problem for that site. And what does boron do? Boron will cause gumming, and that also will increase the susceptibility for certain disease, for example, canker diseases. And we have shoot dieback. So what she found out, when we are looking at boron is different. We don't look at leaf analysis. Actually, we look at hull boron content. So we have to look at the boron. When we have over 300 ppm hull boron content, that means we are in the toxicity zone. And we can see here that among the rootstocks, Lovell did poorly there. At the end of the day, when we look at all those results, what really matter is what? Is the yields, correct? Because we grow for profit. And usually there is so many factors goes into yield, but if we have the perfect conditions, yield will be great. But under certain conditions such as boron, you can see here that the Lovell did poorly. Peach almond hybrids did way much better, and the Viking. And I will show you later on why the boron, I'll use it as example for the resource. Knowing what we know, we generated all that information over 20 years. All that information is in reports, we gave talks, but how can we use all that information in a very simple way that the growers can benefit immediately out of it? First of all, farm advisors in your own county is the best source to go to and ask about this, okay? Secondly, my colleagues, Catherine Jarvis-Sheen, Joe Connell, and Roger Duncan, who did a lot of this great work, put together a very excellent resource. And the resource is a trifold publication in collaboration with the Almond Board and the University of California, Davis Nuts and Fruits Center. So to know exactly the most important or the most beneficial rootstock that fits your conditions, you can find this resource also online. So there is some of it on that table, and you can digitally access it. You go to the Fruits and Nuts Center at UC Davis. You go under Almond. Here to the right, you will see Almond Rootstock Database or the Almond Rootstock Chart, which is this one. On here, that's what the publications look like. There is a description of it here, what we look for, and this is the most important part. Let's say I'm dealing with excessive boron, right? You go here, here it talks about horticultural characteristics. For example, the compatibility, which I said that's the most important part. With compatibility, what I will pay attention, if you are using plum hybrids, you'll see here that it says, okay, where is the Mariana? The Mariana, it will say that it is not compatible, for example, with nonpareil. If we are looking at toxic ions, look here. This is the excessive boron. For example, you will see that all the peach almond hybrids, this is the parentage, okay, they are moderately tolerant to boron toxicity. But look at the Lovell. Lovell is highly susceptible. It tells you exactly what you need to know. If you wish to use the electronic one, okay, electronic database, it will give you actually a couple of things to look at. First, it will put all right, for example, you will see first all the rootstocks, okay? You can access, for example, let's say Hansen 536. It will tell you the Hansen has, let's say, anchorage is very good, suckering is low. I'll give you more information about Hansen if you are looking only for Hansen. But however, let's say I have problems with salts. Let's say boron again. You can come here to the website again. You put the first challenge, let's say boron, all right, and you hit apply. So it will give you all the ones that are suitable under boron excessive conditions. So it's giving us actually here all the peach almond hybrid and giving you the Viking. Okay, I have more than one problem. I have more, beside the boron, I'll give you an example. I'm not gonna talk about biotic diseases or nematode because the next talk is about that. Let's say I have ring nematode. I have boron problem and I have ring nematode, which is mainly associated with bacterial canker and sandy soils. So I go ahead and put boron here. Here it is. I put ring nematode and I hit apply. And what do I get? Viking is your best bet to plant in that soils that have excessive boron and ring nematode problem. So if you plant Viking as a rootstock, most likely that's the best outcome you're gonna have if you have ring nematode and boron toxicity. With that, Thank you very much. If you have any questions, please feel free to email me or now. So, thank you.
Thank you to all of you for sharing your knowledge with us. And we did budget for time for questions. So there are 5 to 10 minutes for questions. So any questions? Okay, this one here. So that we both talked about it before the sessions. I'm gonna try. It's more than one question. It's like 3 questions in one. And they're all very interesting. I think one of your points was, looking into beyond, and I'm just trying to restate so people can hear it too, since I have the mic here. But going beyond prunus genetics and looking into other parental, I think that's a novel idea, and it does require more research. Most of what you see here were different combination of different prunus species. Though to get there was a lot of wild back crossing before. And I think your point why you want to look into that is to go into deeper roots. So we could have a more successful dig excavation and uptake of the different nutrients and the whole water capacity. And that's a novel idea too. And maybe we will be looking into rootstocks that could explore deeper the soil too. And I think your last point compared to the pistachio one is about orchard decay. And I think that's a really good point. You were mentioning, trees last in almonds 20 years and so on, and you have to change them. So looking into orchard decay and how choosing the right rootstock could help you to maybe not replace every 20 years, but replace every 22 years or every 25 years. That will really improve your ROI. So those are things we're looking at. I took the liberty to restate your comments and try to answer them at the same time, since I think part of where your comments were addressed to the Almond board, but also open for you guys if you want to address any of the question or comment.
I'll go. Well,
is that on?
I don't know if it's on, but yes. So this is a complicated question, and again, everything has a life. To increase the life of an orchard, there is so many factors that goes in it. It's you are talking about diseases, and you are talking about environmental conditions. There are so many factors, and to put everything in one rootstock, it's going to be a very challenging task. That's one. Second, when we are talking about CRISPR, that's a great tool. I'm not very familiar with the regulatory issues that is going to come with the CRISPR. So CRISPR can comes with its own package, getting genes from other species or different plants into the almond rootstock breeding program. So that's better addressed by geneticists. But I believe, we can't ignore the regulatory part of it. So regulatory part has to come into the discussion here. So it's a very complicated situation. But let me tell you this: there is orchards that last between 25 to 30 years, which is pretty much like a generation. So it depends how much we are taking care of our orchards. That's one. Second, if we are lucky and not have more diseases or an invasive disease that is going to kill the trees, right? That will be great. But at the end of the day, there is things that we really can't control, and that goes, about the issue when growers are planting in new orchards. There is a lot of unknowns that can come with it, but we can do our best, okay, for that orchard to last approximately. We would like the orchard to last approximately 22 to 25 years, and we are having that right now. So,
thank you. I see another question at the back of the room. So the question was about leaf sampling. If you will delay your classic timing of leaf sample collection, given that this is a later than usual year in terms of phenology and tree growth. Yeah.
The answer to that is yeah, we're seeing in many crops, but also in almonds, that we're about 2 weeks behind. We noticed in our early season, our first leaf sample of the season that normally we sampled that in right around the 1st of May. We did pull some of those and they were premature. They were, the leaf tissue was premature. It didn't give us a good number. So we did delay a lot of that by about a week or so, a week to 10 days. And then, so the normal time to pull leaf tissue is the university is put into, July, the July sample. I know I work for a laboratory, but I think more than one point in the season is important. I think that early season sample is very important because it tells you where you're at, where your nutrients, where your nitrogen is at nutset, and it gives you, we find that tissues that are low in early April tend to drop nuts more than tissues that are high or that are adequate. The sample in July is, it's not a bad timing, but I would almost push that even on a normal year. I would push it back a little bit closer to harvest, depending on where you're harvesting, where you are in the state and when you harvest. The closer you can get to harvest is going to give you more information on what to do post-harvest.
Thank you.
But especially this year, it's going to be very interesting to see where harvest comes, where hull split is, and that may affect, when you want to pull that tissue sample. I don't know if that answers your question.
Well, you can always follow up with him after this session. We run out of time, so I just want to say thank you so much to all of you. And again, a nice segue as I think to the next session is what the resource that Mohammed was talking about rootstocks. He did talk about the abiotic novelties of rootstocks, how to tolerate disease, soil abiotic conditions like salinity. I think next you're going to hear how to tolerate the diseases like Phytophthora, nematodes, etc. So welcome to the next session.